has started.
Welcome back. Today we are going to discuss our discussions on lecture 13. So this is the inverter, and we discuss about the delay. So here, by definition, for the propagation delay is the delay between the input switch to 50% with the output switch to 50%. So here the TPHL is respect to the output. So the output high to low transition. And then the TPLH is output low to high transition. So here the HL and LH is respect to the outputs. And the reason we care about this TP is that it determines the minimal clock cycle. So here the sum of the TPHL and TPLH is a minimal clock cycle, and it is 2TP because TP is the average of those two. If NMOS and PMOS are matched, then the TPLH will be the same as TPHL, will be the same as TP. But if they are unmatched, then in general, we have these equations for the clock cycle. And then the maximum frequency is 1 over of the minimal clock cycle, then it's 1 over 2TP. So this is generally true not only for inverter, but also for any digital circuits. And then we also discuss about the ring oscillators. So when we have odd number of inverters connected in the loop, then it will oscillate. And then the oscillation frequency is given by this 1 over 2 NTP. N is the number of oscillators. Alright, this is a recap of last lecture. And today we are going to discuss how to calculate the TPHL or TPLH. And here we have two methods. So the first method is this average current method. So this is a general method to calculate any delay in the digital circuits. So if you think about delay in the circuit, it is associated with the charge and discharge process out from a capacitor. So if the delay delta T, if you think about the average current flowing through the circuit, I average multiplied by the delay delta T, which is a short period of time. So this will give you delta Q, the charge that is transferred in this short period of time. On the other hand, the charge is given by capacitance multiplied by voltage. So it will be the capacitance multiplied by the voltage change, delta V. So this is generally true for any digital circuits. So you can get the delta T from the C times delta V divided by the I average. So we can use this general method to get the TPHL. For example, here we assume the input has a ideal, perfect rectangle pulse. So at this t equals to 0, the input switch from low to high, and then the output starts from high to low transition, but it will have some delay. So the TPHL is defined as when the output changes from VDD to half VDD, 50%. So this is the delay delta T we want to calculate. So here if you follow the same principle here, I average multiplied by the TPHL will be the charge changed in this process. That is C times the voltage. So initially voltage is VDD, finally voltage is half VDD. So the delta V is half VDD. and the delay is like the delta t here. So you can get the TPHL by moving the I average to the other side. That is CVDD divided by 2 I average. Then the question is how to get this I average. So first of all, this I average is from where? From the NMOS or from the PMOS in this case. This is the output high to low transition. If you recall the previous lecture, we talked about the NMOS's role is to pull down the output. NMOS is to pull down from high to low. So the NMOS is working. This is because the input is now VDD, right? The input is VDD. Then the PMOS here, you know, the VGS is 0. So the PMOS is off. NMOS is turned on, and NMOS is discharging. So this current flowing through the NMOS on average is this I average here. So we want to get this average current from NMOS, and then we can calculate the delay using this equation. Now the question becomes how to get this I average. We need to think about the transistor NMOS operation region on those 2 points. Initially here, this is VGS equals to VDD. For this NMOS, initially this is VDD, and output is also VDD. So this is output start decreasing. So initially it's VDD. So the NMOS VGS here is VDD, and the VDS is also VDD. This is initial point here. So VGS minus VT for sure is smaller than VDS. So you can get the conclusion that initially this NMOS is in the saturation. And then finally, when the voltage decreases to half VDD, then we need to recheck. VGS is again VDD because VGS keep at VDD for this period. But VDS now change to half VDD. VDS is this VO, output voltage, that is VDS here. So it's half VDD. So we need to check this VDD minus VT compared to half VDD. This depends on the actual numbers for the VDD and VT. But in many cases, we will see this is like this. Of course, this depends on the number. For example, the VDD is like 1 volt, threshold is like 0.4 volts, then this is 0.5. So this one will satisfy this condition. But of course, if the VT is very large, like 0.7 volts, then this is not valid. But in the practical cases, the threshold voltage cannot be that high compared to the VDD. The VDD is like more than 3 times of the threshold. So then this is generally true. So if this is satisfied, you know this is the triode or the linear region. So then we know those 2 operation regions. Then we can get the current. So for the initial point, we plug in the saturation current. And for the final point, we plug in the field current equation. And then the average of those 2 currents will give you this I average. Any questions here? Okay, so let's do that. So as we just discussed, this initially we have this saturation current of this NMOS transistor. Initially we have this saturation current, and you know saturation current is half Kn prime, which is like say mu n cox W over L n VDD minus VTN squared. And then finally is the triode equation. So we have this Kn prime W over Ln VDD minus VTN, and then this is the VDS, and now VDS is half VDD. So we have half VDD minus half of half VDD squared. So this is the triode equation for the current. So the average current is the average of those two. So this is the saturation and this triode, and then you can get the average current. Then you plug in the average current into this equation, then you can get the TPHL. So here in the textbook by the Sedgwick-Smith, it has a tedious derivation to reach this conclusion. TPHL equals to this alpha n C divided by this Kn prime W over Ln VDD, and alpha n is a coefficient with respect to those voltages, like the threshold voltage and VDD. So we're not going to show this tedious derivation here, and what is most important here is the approach we use. So let's recap the approach. Delay is related to the voltage change divided by times the capacitance divided by the average current. So here we just need to find out the average current using the saturation current and the triode current. So we can get the TPHL, and this is the NMOS parameters. This is because HL high to low, NMOS pull down, so it is responsible for the high to low transition. And similarly, you can do the TPLH, that is low to high, and PMOS is for pull up from low to high. So here the conclusion will be very similar. The only difference is that you need to change the NMOS parameters to the PMOS, like the Kp over Kp prime and W over Lp, and then the threshold voltage for the PMOS. Of course, here we take the absolute values for PMOS. Then the average of those two will give the TP. So this is a general method to calculate the delay for the CMOS inverter. Any questions? And later we will have one practice on this. Alright, then let's look at the second method. That is the RC equivalence. So to make the problems easier, we can approximate the transistor as a resistor. So this will be less accurate as the average current method, but it will be easier for us as a first order estimation. So here, for example, we look at the TPLH, low to high, okay? Low to high, you know, is PMOS, pull up, low to high. So here, we look at this PMOS, approximate this PMOS with this RP, and then the NMOS will be open circuit, because low to high, the input is like 0, then the NMOS is off. So PMOS is approximated as this RP. And then this is like the first order RC circuit. So the problem becomes this node voltage, which is output, this waveform. When the input change from high to low, then the output start increasing from low to high, but following this waveform. So here the PMOS is like to charge. The PMOS is going to charge this cap by the current. So the voltage here will rise from 0 eventually to the VDD. And by definition, for the TPLH, we look at half VDD. So here, this is a half, 50%, half VDD. And then the delay here is TPLH. So this first order RC circuit, I assume that you have learned this in like 2040, the 2040 class. So it will have a solution like this. The waveform, let's say the voltage as a function of time. So here think about the voltage as a function of time of this first order RC circuit. It will have a solution something like this. Eventual voltage is VDD, and E1 minus exponential negative T over RC time constant. So this is a solution for this waveform when you have the resistor to charge up this capacitor. Here we just need to solve for this TPLH, that is when the voltage becomes half VDD. TPLH by definition is when this voltage becomes half VDD. So we just solve for this TPLH. So here you have this TPLH divided by RC. Then you move this around, it will be move this to the left hand side and then move the half to the right hand side. So it's like this. This exponential term equals to half. So you take the log. If you take the log, then you will have this TPLH RC equals to log half. So this is what you get here. TPLH is negative RC, and here is R is this RP, C is this CL, and then log 0.5, log half. So if you do this log half, you will get this coefficient 0.69. This is log 2, which is the same as negative log half. This is like a high school math. So log 2 is 0.69. So this 0.69 is important. This is a coefficient in front of this RC, which characterizes the delay from 0 to half VDD. And RC, you know, is a time constant. And in this case, TPLH, CMOS is working. So this R is RP. Any question? Okay, then the same approach applies to the NMOS. When we consider the TP-HAL high to low transition, the NMOS is pulling down, the PMOS is off. So we have this RC circuit for the NMOS. And we can use the same approach. So this is starting from VDD to half VDD. And this is the TP-HAL. So we can use the same method to calculate the TP-HAL, but the conclusion is very similar. It's 0.69 RC, and R is this RN NMOS hold down. So this is the same. And then what is this Rn and Rp? So this is an approximation. If we think the transistor is like a resistor, this is not very accurate. So there is no formal equation for this Rn or Rp. So what we can do is to empirically estimate the Rn and Rp for given technology load. So different process may give you different relationship here. But practically in those technology nodes, the Rn is like this 12.5 kilo ohm divided by W over Ln, and then Rp is like 30 kilo ohm divided by W over Lp. So those numbers here will vary depending on the particular process. But as a conclusion here, you can always say the resistance is inversely proportional to this 1 over W over L. Why is that? Because the current, is mu COX W over L, and then voltage terms. That means the conductance is proportional to the W over L. So resistance, is 1 over conductance. So resistance is proportional to 1 over W over L. To make the delay smaller, then we have to decrease the resistance, or in other words, we have to increase the W over L. This is a general approach to decrease the delay. So we have to increase W over L. Any questions?